Jupiter is cool because it's the biggest planet.
It's Spinal Tap. Everything's turned up a little bit closer to 11.
Jupiter is enormous.
And everybody loves 11.
The great red spot, the drama of the poles, of all the vortices going around.
It's got these fantastic cloud layers spinning around, these storms raging bigger than the Earth itself.
And then the moons.
It's like a little solar system in itself.
Instead of a star at the centre with planets going round it, you've got Jupiter with moons going round it.
79 moons, 4 big ones.
Io, Europa, Ganymede, and Callisto. And they are huge.
Each one their own world of ice or rock or volcanoes.
It's a very violent, dangerous, deadly place in the solar system.
You send a spacecraft to Jupiter, you're going to get fried really quick.
Can we send a spacecraft through that environment?
The Greeks weren't wrong to make that thing the king of the gods.
Juno was going to be the first spacecraft to fly over the poles of Jupiter, and it was due to arrive on the 4th of July.
That day, I had my whole family. We were going in to JPL, and I remember turning to my kids in the back seat and said, it might not work. Something bad could happen. NASA and the country and the world are taking a big risk here.
We had no idea what this polar environment was like. We had some sense of the radiation belts. We knew they are nasty. Really, really nasty.
Juno is an armored tank, but it's nothing compared to Jupiter.
So we want to be really careful. Go through quickly and get out.
And so Juno is moving really fast.
It was coming in at about 150,000 miles an hour, which is like going around the Earth 5 times in 2 hours.
Not because we had this incredible propulsion system, but because Jupiter's gravity was sucking us in. The engineers hoped that it wasn't going to get us completely. We were going to just go really close to it. If it doesn't work, it's over. Lights off.
Long before Juno would make its daring attempt, scientists had begun to realize that it was an unusual region of space.
Back in 1955, they detected bursts of radio emission coming from Jupiter. And they didn't know what it was.
It's like a gigantic engine. And the amount of energy that must be just bopping around that thing is amazing.
But this told us that Jupiter has a magnetic field, and perhaps more importantly, a very strong one.
Some planets have a dynamo inside, which means they behave like a giant spinning magnet, surrounding them with a magnetic field. Early on, little was known about what these magnetic fields could do. Then, in 1958, an experiment would begin to reveal the secret.
At the end of the 1950s, there was a huge push in America to have a successful satellite in orbit, and the concept of the Explorer 1 mission was developed. Now, the scientific payload for that mission was led by a person called James Van Allen, who had a big interest in magnetic fields and the particle environment that might be above our heads in space.
One of the things that he was excited about was really high energy particles. And so he proposed an instrument to be on Explorer 1, our very first spacecraft.
And so Explorer 1 had a very simple detector system that would count particles.
It was a Geiger-Müller tube, the kind of thing you look for radiation with. It counts, it does the click, 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 counting for radiation. They wanted to fly this on the rocket to measure the radiation up in space. The experiment was looking for cosmic rays. Now, cosmic rays are the radiation coming out from far out in the galaxy, entering our solar system.
And it went up there and they're counting the particles, zip, 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 going in. At some point, though, the signals disappeared.
At certain altitudes, particularly around about 2,000 kilometres above the surface of the Earth, the count rate dropped to 0.
And they thought, aha, you know what's happening? This is saturated. The number of particles are so high that the detector has just said, I'm going to shut down.
And that realisation actually led to a phenomenal discovery. In space, there are donut-shaped regions around the Earth where there are many, many electrically charged particles, for example, electrons and other electrically charged particles.
The radiation gets trapped into this really lethal zone around the Earth.
And they're trapped because electrically charged particles feel a force from the magnetic field.
We had discovered that the Earth's magnetic field creates a bubble around the planet, called a magnetosphere, that both deflects charged particles and captures some as well. Many of these particles of radiation come streaming from the sun, and this is called the solar wind.
The scientific discovery is, fantastic on the one hand, but it's also slightly worrying because high energy charged particles can pack a punch when they interact with material. So let's imagine, for example, the impact on the human body. If these particles have enough energy, they can penetrate the skin and start to interfere with the cells of the body. So in an extreme case, you might get radiation sickness if you had enough high energy particles coming into your body.
And so we have to be really careful, not just because of humans we don't want to be damaged, but also the electronics.
So can we send our spacecraft to places like Jupiter? Will our spacecraft survive in those kind of environments?
When Van Allen discovered these incredibly high-energy radiation belts around the Earth, I think people started to then look at the models of what would be needed at Jupiter to explain what was being observed. And all of a sudden, like pieces of a puzzle, the ideas started to come together and calculations started to be made, and people were startled because Jupiter was so much more powerful than the Earth. I mean, our radiation belts, as severe as they are and dangerous as they may be, are really a piece of cake compared to Jupiter.
So the first time we left Earth to go out in the solar system, beyond the orbit of Mars, there were major concerns. Can we send a spacecraft through that environment? So we sent 2 Pioneer spacecraft. They were pretty crude, with very limited computational capabilities and very limited power and ability to communicate. So they would just make a few measurements and then send the information back to the Earth. Very simple.
So when the Pioneers flew through the magnetosphere of Jupiter, we didn't know how big this was. We didn't know how large the magnetic field is, and we didn't know how it was shaped or buffeted by the solar wind.
Pioneer 10 was due to fly past Jupiter on the 3rd of December 1973. And these are some of the first images it sent back.
Pioneer carried some protection, but it probably went a little bit closer than it should have. But it was zipping through pretty fast. And in order to try to assess what it was like there, I mean, it basically was carrying a Geiger counter. And I think everybody was startled at the amount of energy that we're talking about.
During its closest approach to Jupiter, Pioneer 10 absorbed 1,000 times the lethal dose of radiation for a human being.
The spacecraft is collecting its worst radiation exposure now. Tension is even greater this time. And so is the relief.
Makes it all worthwhile. After 10 years of having to put up with all these people, the 14 hours a day, it's all worthwhile.
And so after the Pioneers, we knew the extent of the Jovian magnetosphere, and it is enormous.
If we could see it in the night sky, with Jupiter sitting rather far away from us, it would still be roughly 5 times larger than the moon. I always wish it could be like a light purple, traveling through the sky, and it would just be huge.
The solar wind that hits that magnetic field shapes it like a comet and produces a long tail. The tail stretches all the way to Saturn.
The primary purpose of those pioneers was really to say, can we survive this lethal dose of radiation so then we can follow with more sophisticated instrumentation that can do a lot of interesting science. I was lucky to start working on Voyager as a graduate student at MIT. It was the first project that I worked on. I came along just as we were about to launch the spacecraft on its way out, first to Jupiter.
I got a job as an undergraduate assistant to the imaging team. It was a mind-blowing experience in so many ways.
We had the Voyager spacecraft down at the Cape ready to launch, and it was the Pioneer data that made us realize that the radiation tolerance that we had designed into the Voyager spacecraft was not going to be adequate for the environment that Pioneer 10 and 11 had sensed. It threw us into a real turmoil of trying to recover from that.
By the time we got to the Voyager spacecraft, we were already so scared and intimidated by Jupiter that we started to move away from it. We didn't want to get so close because we knew if you got close, you're probably spelling the end of the spacecraft. So you've got to stay away and respect this beast, this monster. It's much more powerful than we are.
Even with a quite small telescope from your backyard, you can look up and see Jupiter on a clear night. And you can see the belts and zones. You can see the red spot. But Voyager saw up close and making a movie as it approached.
And it was really like you were on the spacecraft looking out the window.
You could see these belts and zones, east-west winds going back and forth, and the great red spot being caught up in those belts and zones. And so the weather system was becoming clear. As we flew by, we could get a real sense of how this dynamic atmosphere was working.
As we come in for a close view of Jupiter, you'll see clouds orbiting around the planet at different rates with different thickness bands, and these are called the jets. And these jets go around lines of latitude, back and forth, some faster than the planet, some slower than the planet. And so if you were living on the planet, there'd be these huge shears at different latitudes as these fight back and forth in different directions.
Finding out what causes this wild weather became a key scientific objective.
On Jupiter, the effects of planetary rotation are incredibly important. Why? Well, the strength of the rotational forces depends on how fast the system rotates, and it also depends on how big the system is. And Jupiter's huge.
Jupiter has a diameter of 140,000 kilometers, and it was discovered that the planet rotates at about 40,000 kilometers per hour.
So this body's just completely flying. If you think of the whole planet as a gyroscope, it would be a very big, very fast gyroscope. And those gyroscopic effects dominate many of the dynamics we observe.
We use this demo to explain Jupiter's Great Red Spot, which is a really interesting phenomenon that we've observed for over 200 years, and we think it's existed longer than that. It's essentially a massive hurricane that's about 1.3 times the size of the Earth.
In this experiment, you're looking at a simplified analog of the surface of a gas giant, the cloud layer. It's only about 5 or 6 centimeters deep and a meter across. And we fake the photochemistry with sprayed-in food coloring.
So Jupiter is a very strongly rotating body, but it also has a lot of strong turbulence, and the Great Red Spot has formed from this rapidly rotating turbulence.
Instead of having the massive turbulence that's naturally occurring in Jupiter, by the hand of God, we just mix a little.
As a cloud of gas or liquid moves across a rotating surface, its path begins to curve along with the rotation. This is called the Coriolis effect, and it's what spins hurricanes and typhoons here on Earth. But because Jupiter is so large and turns so fast, its weather is far more extreme.
The effect of the Coriolis force in the presence of turbulence acts to generate large-scale structures like the Great Red Spot, and they persist.
But now what you're seeing in the tank is the formation of these beautiful vortices. And you can see there are all these filaments connecting them. That's what you get in rotating systems. You naturally roll things up into large vortical structures. And they live a long, long time when the system's rapidly rotating. If the planet stopped rotating, that organization would be gone.
The Voyager spacecraft were not just visiting Jupiter in order to examine the planet. The 4 giant Galilean moons were a key objective, and none more so than the mysterious moon Io.
As we were coming in, the ultraviolet instrument was saying, "Whoa, this is bright. Whoa, there's a lot of gas around this environment near Io. You better be careful." Voyager flew by and we saw it covered with volcanoes. We saw gases spewing out hundreds of kilometers up into the sky. And so now we began to make sense what was happening, that these volcanoes were spewing out gases about a ton every second. Those gases were becoming trapped in the magnetic field to make this donut of charged particles. They get accelerated to very high energies. Most of them go out to fill a big volume. Some of them go in, and as they go in, they go to even higher energies and form this very tight environment close to Jupiter, this lethal radiation environment. That inner region is very analogous to the Van Allen belts of Earth, but many times stronger and more nasty. The background radiation here on Earth that we're exposed to is about a third of a rad. At Jupiter, the radiation environment is 20 million rad. We did know Io, Europa, Ganymede are in these orbital resonances where Io goes around 4 times, or every 2 times, and 1 times that the others go around.
The orbits are elliptical, and so when Io is close to Jupiter, it squeezes it, and when it's further away from Jupiter, the squeeze is less. And so you're literally looking at Io going like this. That heat has got to go somewhere.
There had been a paper published in Science magazine that had come out the week before Voyager got there, predicting volcanoes in Io because of this tidal flexing.
But we were not expecting what we saw with Voyager. Everybody thought that Io was the cool, neat one, and the others were, okay.
You know, we knew there was something weird about Europa. It was bright and maybe it had these weird markings, but you couldn't really see them before. And then all of a sudden, there it is, and those first images appearing on the screen, and you know, Europa has all these cracks in the ice and these like lines going across.
They gotta be the Io and Europa, there's a twin.
At that moment, it was just like, whoa. What does that mean?
As an airless body, we kind of expect things to be bombarded all the time, so you end up with a surface peppered with craters, much like our moon.
What about the relief from the crash? Is that practical?
Because the cratering rate throughout the solar system is relatively well understood, the fact that Europa has so few craters is very consistent with it having a young surface, with a surface that has been geologically resurfaced.
Let's see.
Carl Sagan, who was there in the room, he said, Percival Lowell was right. only the canals are on Europa, not Mars. This is something we keep discovering in planetary science. You know, we thought the moons of Jupiter would be old and dead and boring, and they're not, because there's mysterious unknown energy sources. It's like, oh wow, there's more going on here than we thought with our Earth-based assumptions.
The Voyager observations were so spectacular. The dynamics of the atmosphere, the different kinds of moons and what was going on. Everybody said, we gotta go back. But this time we have to go back and stay.
With Voyager, we had a couple of very short, fleeting flybys.
Like, you know, whizzing some pictures out your car windows you drive by, as opposed to actually stopping, getting out of the car and exploring.
We have to go into orbit, send a probe into the atmosphere, find out what it's like inside, go past all the moons and look at them in different directions.
Before the Voyagers had Jupiter in their rear-view mirrors, NASA had been building a spacecraft they intended to go into orbit around the giant planet. The mission was called Galileo.
Galileo had a fitful start right from the very beginning about how exactly it was going to get to Jupiter.
Galileo was scheduled to launch in January 1982 on board the Space Shuttle. The launch date slipped to 84, then 85, and then 86. And then the whole shuttle program suffered a terrible tragedy.
The spacecraft was down at the Cape. I can remember looking out the window of the Challenger launch.
Challenger, go with throttle up.
The significance of that, of course, the loss of life and the disruption of the whole program, but to us was that we didn't have a launch vehicle. And so we packed up our spacecraft and took it back to California, trying to figure out what to do.
Not only was the launch delayed, but after the accident, NASA was understandably more risk-averse. The liquid hydrogen-fueled rocket booster, which was originally planned to deliver the Galileo mission directly to Jupiter, was no longer deemed safe enough.
It was no longer possible to take Galileo straight up to Jupiter, and that's where the mission designers here pulled a rabbit out of the hat and found the so-called VEGA, Venus, Earth, Earth Gravity Assist trajectory that took another 5 years to get there.
We have a go for main engine start. 6, 5, 4, 3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
Galileo is on its way to another world. Fly safe.
After the first Earth flyby, we knew we would be far enough away from the sun that we could actually begin to use the high-gain antenna.
It was like an umbrella. You imagine an umbrella being folded up, and when time came, the spacecraft would fire a device and the antenna could unfold.
So we actuated the motor to free the antenna, and it stuck. You can imagine, and it stalled, only partially deploying some of the antenna. And the motor doesn't reverse. We could tell the antenna had deployed a little bit because the spacecraft's spin wasn't quite the same. It's like if you stick out one arm when you're spinning, you start to do this a little bit. Well, the antenna was doing that a little bit, so we knew it opened some.
So why didn't it open? Well, we understand now that the reason it didn't open was because of the combination of the fact that the antenna had remained stowed for so long and the fact that it went into 2 vibration environments. And when we latched this spacecraft up in California, trucked it down to Kennedy, Challenger didn't work, put it back in the truck, trucked it back to Pasadena, said, let's not mess with that antenna, it was all put together right, we'll just leave it the way it was. Back to the Cape again, so it made 3 trips across the Cape, and the truck was just vibrating the whole time.
And so we did a lot of things. We worked on calibrating how far the antenna was open. Could we use it the way it was? And could we do the cold turns to free it up and see if anything springs free? And we'd know again by seeing the spin rates change if anything broke free. So we spent a couple of years working on those things.
JPL never did get the high-gain antenna to open.
Our capability at Jupiter with the antenna that hadn't opened was going to be dependent upon a single low-gain antenna, and that just meant we had to transmit a lot fewer pictures over the same time, but overall reduction in mission return was large but not disastrous.
The Galileo spacecraft carried along with it a probe, and it's sort of like this size, and it had a big heat shield to protect it around it. And so in July 1995, we launched that probe and sent it in the direction of Jupiter. Now, it didn't have engines, so we weren't guiding it and saying, go there. We just sort of sent it on a trajectory towards Jupiter.
5 months later, on the 7th of December 1995, the Galileo probe was due to arrive at Jupiter. There were no cameras on board, only sensors and the little probe that was going to have an extremely violent introduction to Jupiter.
It was coming in at something like 130,000 miles an hour. It was pulled in by the gravity of Jupiter, and we had to slow it down. And so this heat shield heated up to about 3 times the temperature of the surface of the Sun.
During its maximum deceleration, the probe endured forces of 228 Gs.
And then eventually we kicked off that heat shield, put up some parachutes. And so as it went down, we were able to get a sense of what it was like. What we were expecting was 3 separate layers of clouds. And we went down and said, where are the clouds? Where are the clouds? We're not seeing the clouds. What's going on? So everybody was completely confused. Well, the hint came from the ground. Telescopes on Earth were looking in the infrared at Jupiter at the same time we sent the probe in. And we realized that the probe went into a hot spot, somewhere where there's very little water.
And so I think we realized that our whole idea of exploring these planets with single probes is a little bit susceptible to going into the wrong place.
By the time the probe had got down to about 160 kilometers, something like 23 times atmospheric pressure, it was now starting to get really hot. And so at that point, the electronics is just not working anymore, and it stops communicating and sending signals back to the Earth. What happened to it after that? Well, it was so hot that it basically vaporized. But let's imagine what it would be like if you could be in a pressurized capsule as you get deeper down.
I mean, it's either a hang glider's nightmare or his dream, depending on how risky they want to be.
As you went deeper and deeper, it would get a little calmer, a little less turbulent. The pressure would get higher and higher.
It's so hot, everything's vaporous. Eventually I get down to material that are almost like rock clouds, and they're probably precipitating.
Now, when you get down something like 10% of the radius, you're now getting to the point where the pressures are about 1,000,000 times Earth atmospheric pressure. And the density is getting really high. And at that point, hydrogen changes its phase. It's no longer molecules, protons and electrons connected together, but the protons and the electrons are moving separately, and it becomes metallic. That is, it becomes electrically conducting.
And in this region, you can generate a magnetic field, what's called a dynamo. The fluids convert some of their motional energy into magnetic field energy, into currents. On Earth, the dynamo is very far from us. Earth's core is halfway through the planet. But on Jupiter, you don't even go 10% of the way in, and you've got this 60,000 kilometer radius ball of molten metallic material. And maybe that means it's not amazing that you generate a huge magnetic field.
I suspect it would look like Mercury. A glob of mercury is what it would probably look like.
If you existed, you would be, unbelievably thin, flat-out pancake.
You get to the center of Jupiter, we're talking 4 times the temperature of the surface of the Sun, 50 million atmospheres pressure, and a density that's denser than the heaviest metals that we have on Earth.
Now the Galileo probe had succeeded with its mission and subsequently vaporized inside Jupiter, the mothership had to avoid a similar fate and insert itself safely into orbit.
In just that first pass when we were getting into orbit, Galileo received half of its radiation dose, like 150 kilorads, in one shot. Then it went out further and kind of licked its wounds.
Because of Galileo having this broken antenna, it meant that we couldn't make all the observations of Jupiter that we wanted, the movies and so on and so forth. And we had to be selective, remembering that we don't want to get into the radiation belts too quickly, so we tended to focus further out first. And the first really exciting thing we found was Ganymede has its own magnetic field.
The 7th moon out from the surface of Jupiter, Ganymede, is a moon the size of a planet. Larger than Mercury, it's the biggest moon in our solar system. The fact that Ganymede has a magnetic field means that it might have some ability to protect itself from the harsh radiation of Jupiter, a key attribute for a habitat where life might be found.
So now it starts to open up how we think about even what's a planetary body, right? These moons, how different are they from other planets? They can have their own magnetic fields.
But now the Galileo spacecraft, despite its troubles, was about to make arguably the most important discovery in the history of spaceflight, at the mysterious moon that Voyager had visited 17 years before, Europa.
What we measured as we flew by was something quite remarkable. There were electrical currents that were flowing inside the moon that perturbed the magnetic field. And we concluded that Europa has to have a liquid ocean underneath that ice. And the reason is, ice is not very electrically conducting. You need it to be liquefied as water in a big ocean to carry those electrical currents. Probably has to have salt in it to be electrically conducting, the way that the Earth's salty ocean is electrically conducting.
And the reason why we hardly see any craters on the surface of Europa is because that ocean is squirted out and has filled them in over time. Like Io. Europa, which is also in an elliptical orbit and gets squeezed and relaxed every 2 or so days as it goes around the planet, is dissipating that heat by melting that ice shell. We believe the ocean can be as thick as 100 miles and maybe even thicker. And at the rocky surface at the bottom of the ocean, I know exactly what it looks like. It looks like Io. We call those molten volcanoes on Io, but underneath the ocean in Europa, we would call them hydrothermal vents.
Such vents are also found here on Earth.
And those hydrothermal vents form fields. So it's not just a single chimney, but there's a field of chimneys, if you like. And those fields, we think, on the early Earth and potentially on some moons, could spread across an entire seafloor. And the ones we're interested in, and they are not black smokers, which are kind of chimneys with black smoke belching out of the top. It's a different type of vent. The hydrothermal fluids are warm, not hot, and alkaline. They look almost deserted, but they are chemically active. You have this kind of porous labyrinth of interconnected pores with hydrogen from the vents mixing with CO2 from the oceans, making organic molecules. And here you have a setting which looks an awful lot like the way that modern cells work. And this kind of chemistry was almost certainly behind the origin of life on Earth.
When you look at Europa and you look at the cracks, there is this brown, gunky stuff that seems to be coming from the interior. But also, could it be that there's a source of chemistry coming from Io and Io's volcanoes impacting the surface of Europa, bringing sulfur and perhaps more importantly oxygen into Europa, and that material then gets carried down into the ocean, oxidizing the environment of the ocean and maybe enhancing the life that maybe's there, maybe not, we don't know.
I think that Europa is a place where, given what we think we know about life, there ought to be life.
But it is the most likely place, if you want to go somewhere in the solar system, to find out if there's life. That's where I'd put my money.
After the incredible discovery at Europa, the Galileo mission found that Ganymede also had a subsurface ocean, and there were strong suspicions that Callisto might contain an ocean as well.
We had no idea that life could exist anywhere else in our solar system prior to this. It was just, we have life on Earth, so to get life anywhere else, you need to have planets and other star systems that look just like Earth. And I think we're realizing now that there are other places, even within our solar system, that you can have these right ingredients and have energy and these primordial ingredients that is required to actually make something complex out of randomness, essentially.
Galileo made a lot of incredible contributions to our understanding of the whole system and how it interacts with each other. What was really going on as Io spit out all this material? Ganymede had its own magnetic field. Europa had an enormous ocean.
But by then, we'd kind of done what we were going to do with Galileo.
And the radiation at Jupiter is very, very hard on electronics. So it upsets the spacecraft. It goes into safing, stops all the sequences, and you have to restart things.
After having its mission extended 3 times, it was eventually decided in 2003 to dispose of the aging, radiation-damaged spacecraft by flying it into the clouds of Jupiter.
We learned so much from Galileo. In fact, it was really the results of Galileo that led us to Juno.
Liftoff of the Atlas V with Juno on a trek to Jupiter.
The big question after Galileo was, did that probe just go into somewhere weird, or was the lack of water symptomatic of the entire planet? Now, this is extremely important.
In 30 minutes that it took the probe to go into Jupiter and get this data, every theory of solar system formation was proven wrong.
Because remember, we think the gas giants formed by having giant snowballs, say 30 times the mass of the Earth, that pull in the hydrogen to make the gas giants. So at the core, we think there was ice. And yet, when we went in with that probe, we didn't see any, or very little. So what's going on?
So when Juno came along, one of its primary objectives was to go in and see how much water and oxygen is in Jupiter.
We have to go back and find out. And we could send in 100 probes, but that's going to be expensive and difficult. And we thought of a cleverer way of doing it.
Juno was designed in order to make measurements almost over the whole planet and look at the water rather than in one spot. And to go much deeper, remotely, not with a probe.
The brilliant idea was to use microwaves. Everyone knows that microwaves are absorbed by water. So what we want to do is fly over Jupiter and map out the distribution of water from the absorption of those microwaves. But to find out what it's like deep inside, we have to measure the distribution of mass inside that changes the gravity field in some subtle ways.
And to do that, we had to go into a polar orbit. And we also had to get really close.
Now remember, we've got a problem with Jupiter. Jupiter has these radiation belts around it. You don't really want to take your sensitive electronics of your spacecraft through that environment, at least not for long.
We had to somehow get beneath the radiation belt. If we can just thread that needle. I was just praying with my eyes closed, that this was going to work. We were getting a few thousand miles above the cloud tops when we were doing this maneuver. Nothing had ever been that close.
Fire the engines.
Go ahead, Nav. Yeah, we see the engine has started.
35 minutes, they're firing away, slowing down the spacecraft, so it gets caught in Jupiter's gravity. And when we find out the spacecraft's alive, whew, big relief.
Juno, welcome to Jupiter.
NASA did it again.
And you know, the thing that was also sobering was we were coming back. This was our game plan. Every orbit, we were going to have to run through that fire with our bare feet.
Juno carried a camera called JunoCam, designed to provide pictures for the public back on Earth. But these images were to reveal a great surprise.
Our view of Jupiter before Juno was from the equator. So then when Juno flies over the poles and is looking down, and there we see these vortices, all this structure is just extraordinary. The JunoCam, that little camera that was just slapped on to get some publicity photos, has turned out to be just extraordinary.
I'd love to say that I figured this out and did it on purpose, but really what I wanted was a great picture. Little did we know that the poles of Jupiter were going to become this huge science discovery by itself. Giant polar cyclones. Nobody anticipated that.
With the help of the citizen scientists around the world helping us process those images, we are seeing all sorts of little structures and pop-up clouds. And nobody expected that level of detail. When we fly in close, measuring the perturbations in Juno's motion, we're beginning to get a sense of what it's like inside. And what we're finding is that it's not like the textbook picture where you have a metal rock core inside and then a layer of hydrogen and then a layer of gas above. It's much fuzzier, much more mixed up. And so in fact that core is spread out to about 40% of the radius. So it's mixed in with the metallic hydrogen. You're beginning to see that the convection system we see on the outside extend a long way in. They're much, much deeper.
But what Juno has not yet been able to explain is what drives the jets. It might be that turbulence at the surface drives these jets, and then the jets burrow down into the depths. But with Jupiter, so much heat is coming out of the interior of the planet that maybe the jets are being driven by deep motions, and it's their surface expression that we're seeing at the top.
And there's probably something deep down is driving a lot of motion inside of Jupiter.
And so we're beginning to think about that region where hydrogen becomes metallic, that generates this strong magnetic field.
The magnetic field is probably moving things around, driving convection and eddies and all kinds of motion. And so somewhere there's a balancing act. The stuff that's coming in from the top meets the stuff that's coming up from the bottom, and all hell breaks loose.
What's the right answer? We do not yet know. Open question. One of the great questions for me as a scientist looking at Jupiter and studying Jupiter.
Nobody really knows for sure what makes the colors in Jupiter's zones and belts. We see all these oranges and reds and beautiful yellows, right, and browns, and Io is spewing out tons of sulfur, among other things, because it's volcanic. And models sort of indicate to us that as I radioactively change sulfur, it can make these reddish hues. And so Io may have had a huge effect on the way Jupiter appears to us, but it's producing a lot of material that's definitely going into Jupiter, and it may be part of the reason that Jupiter is this incredibly beautiful object. So in many ways, the combination of Io and its volcanoes with Jupiter's strong magnetic field is really at the core of an engine or a generator. When we laid out the objectives of Juno, it was to go sort of figure out the puzzles of what it was made out of and how it formed. Nobody really conceived of the idea that we'd go there and the entire structure was going to be different than we thought. It may be that we've been a bit naive, that if Jupiter could throw us this many curveballs, that our ideas of how stars work could be kind of wrong too. I mean, there's even more energy, and they're even more massive.
Astronomers have looked out and seen many stars, right? Billions and billions. Many of those are binary systems, two stars going around each other. Sometimes there's a big star and a little star, maybe a star that has only a tiny bit of fusion inside, like a brown dwarf. In our case, and many others we've seen, where we have a star and a planetary system, the biggest planet does not have enough mass to have a fusion reaction inside. So let's think of our solar system, where we have the Sun and we have Jupiter. And Jupiter is 1,000th the volume and 1,000th the mass of the Sun. And so it's too small to have fusion inside. It's a failed star, but it's a very successful planet.
Juno continues to explore Jupiter, diving beneath the lethal radiation belts on every daring orbit. And each time, we learn a little more about the greatest planet in the solar system. But we have unfinished business with some of its moons.
JUICE is the next major exploration mission for the European Space Agency. Jupiter Icy Moons Explorer. Its sole purpose is to go to Jupiter and explore the icy moons. The main aim is really to try and understand what they look like below the surface. How thick is the ice layer? How deep is the subsurface ocean?
NASA has been funding a mission called Europa Clipper, which will take a number of flybys of Europa to try and get a deeper investigation of what might be happening on the surface, even a basic understanding of some of the chemistry that might be there, in preparation for investigations yet to come, getting down to the oceans.
For places like Europa, Ganymede, getting below the ice layer is the holy grail, right? Getting into that subsurface ocean, that is a whole new frontier, and that will be a fascinating thing if we can ever achieve that.
Well, the first challenge you have is actually getting down through the ice. And while people have talked about drills and other such things, we want to reduce this 20 kilometers of ice as much as possible. And so we've built submersibles that can actually navigate through tunnels and canyons to be able to try and make their way down through perhaps these open crevasses as close to the water as possible. Now, if we can get into the water itself, we've built a buoyant rover that goes underneath the ice and floats. So it drives on the underside of the ice, exactly at that ice-water boundary on there. And by turning a camera to look up at the microbes that we might find there on the underside of the ice. And then we've been working on deep ocean vessels where we hope to go down to the bottom of the ocean on Europa and then bring back samples to us of what might be down at the bottom of the ocean.
JUICE doesn't launch till 2022. It's not going to get there until 2030.
In the mid-2020s, we hope to launch Europa Clipper, and after a 6 to 7 year voyage, we'll reach Jupiter itself.
Some of the people already working on it now will have retired. Some will probably have passed away. What I love about it is that there's this generational feeling to it. By the time we get the data, there will be another generation of scientists looking at it.
There is an immense opportunity for us to find the first signs of life beyond our world in these warm, watery, rich environments that we are just beginning to see that we can even access. And the rovers that we're developing and that are testing here on Earth are only the ancestors, the far ancestors of what we might eventually send there.
So perhaps one day we'll discover life residing under the ice, a precious habitat thriving despite the brutal radioactive environment, in the shadow of the mightiest planet in our solar system, Jupiter.